Hello, everyone. Welcome to our session. And this session is about unlocking how to efficiently, flexibility, and manage the 7 AI chips in Kubernetes. It's a rather abstract title, but in one sentence, it can be sound like how to improve your GPU utilization in Kubernetes. Yes. This session is brought to you by 2 software engineers. My name is Mengxuan. This is my colleague Zhang Xiao. We are both from a new founded company called Numa-aware. And here are let me first introduce to you the background. The first background is the burst requirement for computing power. The global GPU marketing growth is over 60% than last year. The majority growth is Nvidia, and the Heterogeneous is over 20%. As you can see in this figure, it has been rather boosted after the emergence of large language models. And you may guess we are from the mainland China, so in our country, the high-spec Nvidia can't be imported very easily. So we have to use alternative cards like these device vendors. They are all some alternative plan for Nvidia cards. And of course, they are not as high-spec as Nvidia, and the user experiences may not be as good as Nvidia, but it is very cheap, so we can use them in the production level as well, and it has a decent performance. Yes, but here we meet a challenge, is that the GPU can't be shared in a traditional Kubernetes. Suppose you have 5 GPUs, each with the capacity of 40 G device memory, and it is all running a 2G little model, small model, and it will cause all the device not be able to fit more pods other than this one. So the other pods which uses GPU are in a pending state, which causes the utilization of the GPU in the cluster is very low. And another challenge is the management of heterogeneous clusters. As you can see, there are multiple device vendors in China, and many of them implement their own scheduler extender. And it hijacks the filter, hijacks the score process, and if you have a cluster composed of multiple AI cards, then you have to install their scheduler extenders, and you have a more scheduling pipeline. And if you enter the filter, you have first to go through the multiple extenders and go back to the filter, and then into the score process, you still need to go through all the extenders and return to the score. This will cause the performance of the Kubernetes scheduling is very poor. That's a problem needs to solve. And one kind of solution is DRA. This is called dynamic resource allocation. It is an API for requesting and sharing resources between pods and containers inside a pod. It is stable in 1.32 version in Kubernetes, and it is you need to set a resource claim and a resource class, and every device vendor need to implement their own resource DRA driver, and it communicate with Kubernetes to do the device sharing and scheduling and allocating. But it has many restrictions. The first is it requires the Kubernetes version must be the latest. It means 132 Kubernetes, and it happens to me that not many device vendors implement DRA driver. For now, the Nvidia DRA driver is under construction, and it's not production level ready. So you have to maybe use this feature in the future for it to enter the production environment. And also, it needs to create resource claim and resource class. If you want to share the GPUs inside the Kubernetes, you have to configure this whole. You need to use the resource claims here, which is defined here, and the corresponding resource class defined here. It has all need to be applied in Kubernetes. Yes, and still this feature is not enabled automatically. You need to enable it explicitly. And another solution is what we brought here. It's called HAMi. HAMi is a heterogeneous AI computing virtualization middleware. It is it is used to provide GPU sharing and manage multiple heterogeneous AI computing devices from multiple device vendors. It is composed of a mutating webhook, a scheduling extender, and the corresponding device plugins for each of the device vendors. And we have additionally in-container resource control for each of these devices. Yes, and it is a pluggable, non-intrusive, standard, and lightweight, which means you can HAMi install and HAMi uninstall very easily. And it is a CNCF sandbox project. And the key feature of HAMi is the device share, advanced scheduling, and unified monitoring. Device share is our key feature. Let's show here. If you have a node composed of 4 GPUs, and you have 2 users, each of them submit a task which uses 2 GPUs, without HAMi, you need to allocate. You have to use 4 of them all. And the overall utilization is less than 50%. And with HAMi, it can be observed that these 2 tasks can be shared on 2 GPUs and leave the rest for other tasks to use. So it can improve the GPU utilization to nearly 100. Yes, and it is transparent to task. You don't need to modify the task. You don't need to modify the image or the source code or anything. Just specify the device memory you need to use is okay. And this is the device share insight. This is how we control the device limit inside the container. We inject a library called HAMi core inside this invocation line. It hijacks calls from the CUDA runtime to CUDA driver. So we can do the counting here. We know how exactly are the device memory allocation inside each of the container. If it passed the limitation you set in this, inside this task, it will return an OM error. Yes, it applies to wider range of Nvidia and Kubernetes. The only requirement is your CUDA version is greater than 10.2, and the Nvidia driver version is greater than 440. Yes. And this is how we use HAMi. You simply need to specify the number of GPUs you wish to see in this container, and along with the GPU memory you wish to cut for this container. In this example, you said this task needs 2 GPUs, and each GPU uses 10 GB device memory. And the scheduler sees that, and it will cut the 10 GB device memory for this task, and leave the other 22 for other tasks to share. And we provide the in-container resource control. You can see the Nvidia SMI inside the container. The upper limit of device memory is limited to 10 G device, 10 G. Yes, you can't use beyond that. It is according to this. Yes, we guarantee that the upper limit is contained in this container. Yes, and other features include that we can support the device specify. You can specify the type of GPU you wish to use. If you only want to use A100, then you can set the annotation of the task here with the use GPU type annotation, which means if it is assigned to A100, then you can only be applied to A100 cards, or you can avoid being applied to A100 by set this blacklist no use GPU type here. And we have another feature called task priority. The method to use it is very easy. You simply specify an environment variable here called CUDA task priority. For now, we support 2 types of priority. 0 is the high priority, and 1 is the low priority. The difference is that as long as the high priority pod is submitting kernel to the certain GPU, the low priority pod will be temporarily suspended and wait for this high priority pod to stop submitting new kernels to GPU, and the low priority pod will be resumed running. It is all transparent to the task, and it is very automatically. Yes. And we also support dynamic MIG feature. You can use it like the examples in this page. You simply need to specify the number of GPU you wish to use along with the device memory you wish to allocate. You set the number and memory here, and we will search according to the templates here, and we will find the most fitting make instance for you to use. And we use NVIDIA Make-Parted to dynamically generate the make instance for certain card. So the users doesn't need to really know the make instance name like 1G, 10GB, because it is different for different types of NVIDIA card. The user only need to concern how many GPUs it wishes to use inside the container, along with the device memory it wishes to use, and leave the rest for us. Yes. And we can apply this device memory control to other devices other than NVIDIA, like Accent. Yes, this is a Huawei manufacturer AI chips. Yes, if it is 64 GB in total, and in this example, we limited to 16G, and you can see here it has been limited. And it also applies to inverter and Cambrican devices, just like Huawei and NVIDIA. Yes, and this is other scheduling features we HAMi introduces, like the NUMA and topology-aware. If you want to allocate more than one GPU, like you want to deploy an AI training job across multiple nodes and multiple GPUs, then you probably wish to minimize the communication cost between multiple GPUs. And for that reason, we can observe the topology inside between each GPUs along with the network topology. So by doing that, we can allocate the nearest GPU for this AI training job to minimize the communication cost. Yes, it has been applied to NVIDIA, Accent, and this Matex device, yes. And we have another binpack and spread scheduler policy. It is for each task. Each task can specify their own scheduler policy. And the binpack means it wishes to allocate to a GPU which has already have the task running on that GPU to minimize fragmentation caused by a GPU share. And the spread is on the contrary. It wishes to allocate to a GPU where no pod is running on that GPU to maximize the performance. So each pod may have their own request it may have their own scheduler policy to best meet their feeds. Yes, we provide the binpack and spread scheduler policy for GPU level and node level, yes. And after we introduce the GPU sharing, there are many things you need to monitor other than the DCGM exporter matrix used to you by the DCGM exporter, like how many device memory has been allocated for a certain GPU, how many device memory are still free, still available for other tasks to use, and how many workloads are running on that GPU, and how many workloads and their corresponding PI pod name, container name, and etc. They are all contained in this form of matrix exporter, which can be easily integrated into the premise use and later be demonstrated by the Grafana dashboard. Yes. And the Volcano vGPU is supported by HAMi. If you use Volcano, if you go to their Pavella project, their slides has pages about the Volcano vGPU, which is contributed by us. And the HAMi community is responsible for the in-container resource control and leave the rest scheduling process for the Volcano scheduler. You can easily find their the Volcano vGPU document on the Volcano vGPU project, on the Volcano project. And it's the same about the coordinator. We also integrated GPU sharing mechanism into the coordinator. You can find their document on their website. Yes. Okay. Allow me to pass my phone to my colleague to introduce the adopters, the roadmaps, and the summary. Yes. 你直接说。
Hello. 能听到啊？可以听。Okay. Thank you, Mengxuan, to introduce the HAMi architecture and the GPU sharing and the advanced scheduler. Let me introduce HAMi ecosystem and the adopters. From now on, HAMi support, in addition to Nvidia, we also support such as the Azula and the Cambrican and the more threads and Metax, the other 6 AI chips. And also, we want to support more AI chips. From the AI chips, where the Kylin OS operator system also supports the HAMi to build in the AI system. And in China and around the world, many vendors also build in HAMi to their product, such as the DaoCloud and the Silicon Cloud and the uCloud. The uCloud is the China biggest the natural cloud provider, and some virtual users also use HAMi to solve the GPU utilization. Their situation is the GPU utilization very small, such as the South Carol company, and use HAMi to combine train and inference in their production situation, and such as the travel company and some key users such as the PNI security and the ICBC, also the bank and the business company also use HAMi to maximize the GPU utilization and the unified management, the heterogeneous AI chips. So from now on, we have nearly 100 end users from around the world. Okay, so this year, HAMi also becomes the CNCF sandbox, but we also have a clean roadmap in the 2025. Firstly, we will support more the heterogeneous AI chips, such as the Kunlun, and we also want to support the AMD, Intel, or the AWS. So, any helps, we will welcome. And furthermore, we also want to support the DRA, but it's more challenging how to have a compatible way to integrate it with DRA and the HAMi, because many end users use HAMi to their production environment, but from now on, and many AI chips company have don't the DRA implement. So also we will create a HAMi web UI for easy to use, and maybe in the end of the year we will propose it to the incubating project. So yeah, and the dynamic MPS for Nvidia. And if you want to join us, we will very welcome. Yeah, this is our Slack and the GitHub repo. Yeah, we all finished our talk. Any questions? We welcome.
Okay, any questions? Okay.
Yeah.
Yes.
What are the challenges for doing that? Is it expected in December?
The biggest challenge is that the communication we can't reach it to the AMD. Yes, yeah. That's the biggest. If we can reach AMD, I think this can be easily implemented. Yes.
We want to keep in touch with the AMD open source strategy or the software department, but it's difficult to ask. Yeah. Okay.
Could you say a bit more about how you do this scheduling, maybe? So how things like pod migration, or what happens if a node goes down that a pod is running on? These kind of questions.
Okay, the scheduling part is we implemented our We implement our own scheduler extender here. And the HAMi is composed of a mutating webhook, a scheduler extender. And we do the scheduling here. We implement the filter and the score process. Yes, we do the additional GPU filtering and GPU node scoring here in the scheduler extender. Yeah.
So is it a regular scheduler plugin, as in the plugin framework, or is it a completely separate scheduler?
It is a scheduler extender. It's not a scheduler framework, because if we adopt the architecture of the scheduler framework, you have to compare every Kubernetes scheduler version from 1.16 to 1.32. It is difficult for an open source project like us. So we use the scheduler extender for using that. It can be easily inserted into every scheduler version from 1.16 to 1.32. Yes. Okay. Any other questions?
Have a nice day. Bye-bye.
Have a nice day. Yeah.